evidence for e to the x. I've already mentioned this remarkable result.
Let's define a function f of x, which is equal to the value of this power series, the sum n goes from 0 to infinity of x to the n over n factorial. Now earlier, we've seen that the radius of convergence of this power series is infinite. So this power series converges regardless of what value I choose for x. So this is a function whose domain is all the real numbers. Now the big result here is that this function, f of x, ends up being equal to the more familiar function, just e to the x.
Let me now try to convince you that this is true.
Well, first of all, f of 0 is what? Well, what happens when I plug in 0 for x? Then all of these terms vanish except for the n equals 0 term, because by convention 0 to the 0 is 1. So that's 1 over 0 factorial, that's just 1. So the value of this power series when x equals 0 is 1. And note that that's also e to the 0th power. That's also equal to 1.
Not only do these functions agree at a single value, but they also satisfy the same differential equation.
Well, let's see. So let's look at e to the x. What's the derivative of e to the x? Well, that's itself, right? So e to the x is a function which is its own derivative. Now let's take a look at the derivative of the power series, the sum n goes from 0 to infinity of x to the n over n factorial, right? I'm really just asking what's the derivative of this function that I'm calling f. Well, I'm differentiating a power series, and I can do that term by term. So the derivative of this power series is the sum n goes from 1 to infinity. I can throw away the n equals 0 term because that's a constant term and the derivative of a constant is 0. So it's the sum n goes from 1 to infinity of the derivative of x to the n over n factorial. So now I just have to differentiate each of the terms separately and add all those up. So this is the sum n goes from 1 to infinity. What's the derivative of x to the n? That's n times x to the n minus 1. And then the constant is just n factorial. But I can simplify this. This is n times x to the n minus 1 over n factorial. That is the same as the sum n goes from 1 to infinity of n over n factorial. That's just n minus 1 factorial in the denominator. And the numerator is x to the n minus 1. But now if you think about what this series is, when I plug in n equals 1, that's x to the 0 over 0 factorial. When I plug in n equals 2, that's x to the 1 over 1 factorial. When I plug in n equals 3, that's just x to the 2 over 2 factorial. When I plug in n equals 4, that's x to the 3rd over 3 factorial. This is actually the same as just the sum n goes from 0 to infinity of x to the n over n factorial. So what I've shown is that f is a function which is also its own derivative, just like e to the x. Because if I differentiate f, if I differentiate this power series, well, what I get back is just f again.
Two functions, both alike in dignity. These two star-crossed functions agree at a single point, and they're changing in the same way. And consequently, they must be the same function.
And therefore, f of x is equal to e to the x, right? What I'm saying is that e to the x is the sum, n goes from 0 to infinity, of x to the n over n factorial.